Thank you very much for the invitation. It's great to be here, and this introduction also saved me. I want actually to mention some of this, what was mentioned by Havna. Okay, all right, so let me begin my presentation. So I will talk about my dissertation research. My dissertation research can be broadly characterized as intelligent information retrieval, and by intelligent here intelligence means that we aim to incorporate basically ranking stage relevant signals directly into retrieval by using generic k-nearest neighbor search algorithms. So this work, as was mentioned, is supported by the following NSF grant, and an important byproduct of this research, as well as the main research vehicle, is a generic and efficient library for K-NN search, codenamed NMSLeap. And I developed this library jointly with other people. In particular, I greatly appreciate contributions from Bilek Naidan, Yuri Malkov, and David Noy. My work consists in applying generic nearest neighbor search algorithm to ad hoc text retrieval. So this is, in my opinion, an interesting and not only in my opinion, a challenging task, which is at the intersection of natural language processing, information retrieval, and algorithmics. But before I dive into details of my dissertation research, I would like to briefly overview some of my other projects that I worked on recently. Before joining CMU, I was a staff scientist at the National Library of Medicine, where I worked on the search engine PubMed. In particular, I designed, prototyped, and helped develop a production version of the new or an updated version of the rank retrieval algorithm, which delivered a 15x improvement in efficiency without any loss in accuracy. Concurrently, I participated for several years and tracked web ad hoc task, and for 2 consecutive years we submitted best category B runs. I then worked on.
Sorry, Lou.
Yes.
I'm just curious. What is the web ad hoc task, and what is category B?
Well, ad hoc is basically ad hoc retrieval, but kind of web scale. But we didn't have enough resources because it was a personal project. It wasn't related to my work. So we basically had to use a smaller 50 million subset. So, yeah. And by the way, feel free to ask questions. I should have mentioned this. Yeah, interrupt me whenever you have a question. So, yeah, it was a small subset, but in fact, for the last year we participated, it was the second best overall. It's not, these track evaluations, they are not like Kaggle-like competitions where you have thousands of participants sometimes, but it's still challenging to get good results because you compete against people who have been doing this for sometimes dozens of years, like Robertson, for example, or Terrier team. Okay, all right, well actually that was super fun. And then I worked on lightweight compression for information retrieval, and actually I'm very proud of this project because I think it was the first published work where we could develop an algorithm that decompresses / decodes integers, billions of integers per second. And it was also the first algorithm that could decompress integers with the speed of reading from memory using a single CPU core. Okay, I also worked on the reliability of IR experiments, on metaphor detection, and participated in the development of domain-specific question answering system. While the last project didn't produce any publications, but I still got a lot of useful experience with QA systems. To further motivate the discussion, I would like to present you an example. I want to motivate the discussion with an example from the domain of factoid QA. So assume that you have an unstructured text collection and you want to build a QA system. Well, a factoid QA system that would be able to answer questions like this one: who released an animated adaptation of Goldilocks in 1922, right? So which approach would you use? Well, here's one algorithm or method that you can use. It's famously dubbed as deep QA, although it is actually largely based on the ideas pioneered by the proto-syntax system developed in the 70s. So such a system would analyze a question. It would extract search queues, which are important keywords and key phrases. It would also try to determine, and this is really important, the type of the question, the expected type of the question. So in this case, it's a person. And then it would use the retrieval module to find passages containing these keywords and key phrases. And here is an example of what such hypothetical system might retrieve. And as a last stage, it would try to extract/generate answers from the passage, from the retrieved passages. And this step usually relies on named entity recognition with subsequent comparison of types of extracted entities against the expected type of the question. This is a really well-known algorithm. So assume that our hypothetical named entity recognizer found two-person mentions, and here it is Disney and Goldilocks. And so we assume that either of them might be an answer, but don't know exactly which one. We can further use heuristics that the answer shouldn't appear in the question. Normally, it doesn't happen. So then our system would say that the answer is Disney, and that's in fact the correct answer. And this approach, where we first determine the type of the question and then generate answers that match the type of the question, is called type and generate. It can be really fast. It can be easily coupled with the IR module, but it's also very brittle. And the reason for this is because it happens because named entity recognizers, question typing modules, and everything related to NLP is actually quite inaccurate. And in fact, if you try a real named entity recognizer on this passage here, Disney would be an organization. So, and if you use such, if you use type and generate and real named entity recognizer, then the search algorithm, our QA system wouldn't be able to answer this question correctly. And for this reason, the IBM Watson team, when they developed the system, they chose a different approach, which is the opposite. It's called generating type. So it consists in using a much larger number of answer candidates, basically every possible named entity, maybe some noun phrases. And these are, typing is deferred to the very last, basically, ranking stage. So but this algorithm can be much more accurate, but it's also much more expensive. So on one side of the spectrum, we have fast but brittle type and generate, and on the other side of the spectrum, we have more robust but apparently much slower generating type approach. And I would argue that instead of reaching for this extreme, we need to achieve some middle ground solution. Oops. All right. And so how would we achieve this middle ground solution? I would argue that one should do more work during retrieval, and in particular by incorporating relevance, ranking stage relevance signal into retrieval. However, there is an efficiency issue because as we keep adding these complicated, more expensive to compute signals to the, basically incorporating them into retrieval module, as we add more and more of such signals, the retrieval becomes less and less efficient. So at some point, we wouldn't be unable to use a simple TF-IDF based retrieval, which is in fact a simple form exact KNN search using the maximum inner product similarity, and we would need at some point to replace it with more generic and more flexible algorithm for KNN search. Okay.
So
Yeah.
can you go back?
Yes.
Actually, can you even go back one more? The one thing that I'm not clear on is, right, the way I'm used to thinking about something like your first example is that what you get back is an answer as opposed to a sentence or a document, right? Are you thinking about this differently?
Sorry, can you repeat this?
In this context, what is the output of the system?
Oh, okay, good point. I should have probably been more clear about this. So this is factoid-based QA system. So the output of the factoid QA system is typically a named entity, right? In some cases, it's a noun phrase. But it's much harder to deal with noun phrases because there are so many of them. But it's much easier if you know that the output, that the answer is, person's name, like some famous person. This is why actually it's easier to deal with quizzes and yeah.
Right. So the part that I'm confused about, if you go to the next slide, then when you're talking about intelligent retrieval and so on, what's being retrieved? An entity, a sentence, a document?
A passage from which we would extract an answer.
Okay, so it's not solving exactly the same problem. There needs to be some post-processing.
Yes, of course. Yes, okay. Absolutely. And I have to emphasize that I deal only with the candidate generation module, and I want to improve performance of the candidate generation module. So it's not especially brittle, but it's not as expensive as simple approach where we defer everything to the last stage.
Got it. And then the second thing I didn't understand is you're saying something that's a little bit subtle about the equivalence or relationship between TF-IDF and k-nearest neighbor search. I think we're going to go into it later, but it's not obvious a priori that these are the. I think you were saying that TF-IDF is some kind of special case. Of
yes, absolutely.
Yeah. So can you just elaborate that?
Yes, that's a good question. Well, I'm skipping some of the technical details for the sake of time, but basically TF-IDF, if you compute like similarity like BM25, it's what you essentially compute. It's the inner / dot product between a query vector and the document vector. And in most cases, we actually do it exactly. And when we have a short query, actually I'm going to mention it later, we have a short query and a sparse query document matrix, we can do it really efficiently. But if we hand really long query, it stops being efficient. Or if you build a complicated linear model where you include a lot of relevant signals, and then this sparsity doesn't help you anymore. Basically, it becomes an exhaustive brute force search. So exact search methods stop being efficient. Okay, is it clear?
The question I was asking is, what's the relationship between nearest neighbor search and TF-IDF? It's not a priori, it seems to me that there's no relationship.
Yes,
they're equivalent.
They're equivalent. I mean, special case. It's a special case. It's exact nearest neighbor search, which is basically the maximum inner product search, because you compute the inner product and you find entries that have the maximum inner product, or say 100 entries that have maximum inner product. Okay, is this clear? Okay. All right. So I have to admit that using ranking stage relevant signals, embedding them into retrieval is not a new idea. And so this line of research is in fact related to the work of other people. In particular, it is related to the statistical machine translation-based query expansion approach by Stefan Riesler. It is related to automatic coupling for AR, which was proposed by Alan Ayais, Shuchen Yao, and Peter Clark. And it's also related to structured information retrieval, which was advocated by Matthew Bilotti, Paul Ogilvy, and several other people. But what is nice here is that KNN search can be a unifying paradigm that actually encompasses several ways of doing coupled and structured IR. Oops, sorry. Okay, so by applying these generic KNN search algorithms, we aim to achieve 3 objectives. So we have 3 hopes. We hope that we will be able to find documents relevant documents that are hard or unable to find using standard TF-IDF retrieval, simply because that's a very simple similarity that does not reflect all the complexity of the language. We hope that this may permit an effective separation of labor between data scientists focusing on accuracy and modeling and software engineers focusing on efficiency and scalability. And we also hope that using KNN search, generic KNN search, will allow us to achieve better efficiency effectiveness trade-off. Unfortunately, KNN search is a hard problem that in many cases, it's a hard problem if we deal with high-dimensional data. And in many cases for high-dimensional data, due to the curse of dimensionality, we cannot retrieve things both efficiently and accurately. In some rare cases, we do have computational shortcuts, as in the case of TF-IDF search, where we have sparse query document matrix. But we believe that in general case, these shortcuts do not exist, and the curse of dimensionality cannot be fully removed. But we can apply a magic of approximation to weaken this curse. And approximate search methods can be much more efficient, although at the expense of losing some of the relevance answers. And this creates additional challenges because to replace or complement, say, TF-IDF-based retrieval with generic KNN search, we have to achieve two challenging objectives. First, we need to design a simple yet effective similarity that would beat a baseline method such as BM25 by a good margin. And I illustrated here by showing that the set of relevant documents, that this green circle returned by this exact KNN search using this good similarity, is much larger than the set of documents found by BM25. But we have to apply approximate search. So it may be the case that the set of documents retrieved by this approximate method is much smaller than the set of documents retrieved by the exact method, and that can actually be smaller than the set of documents retrieved by even BM25. And that's something that we don't want this situation to happen. To avoid this degradation by approximation, we need to achieve our second challenging objective. We need to implement really efficient and accurate algorithms for KNN search. So first objective, design an effective similarity. To design effective similarity, I played with two types of models. At first, I considered sparse bag-of-word representation and a similarity where I linearly combined BM25 scores and scores of log scores of IBM Model 1. There is prior work showing that this solution can be really, really efficient. And I also played with I played with dense representations, and in particular with average word embeddings, where similarity is computed using simple cosine similarity. And I assume that everybody knows about average word embeddings. So I won't talk about this in details, but I would like to say a few words about IBM Model 1, because that's an old one technique. And in particular, because it was so effective in my experiments. So
How constrained are you in the models you're able to choose that you can actually use in the retrieval?
That's a great point. Yeah, I think we are less constrained. The answer is that I don't know this, of course. It's an empirical question. We're less constrained than in terms of that we can do much more than TF-IDF, but
But you can take an arbitrary model.
No.
And
No. It has to be pretty much bag-of-words model. Okay. All right. So what IBM Model 1 is a token-level translation model as opposed to, say, phrase-based translation, which is trained using a parallel corpus and expectation maximization algorithm. One good example of the parallel corpus that is relevant to our discussion is a set of question-answer pairs extracted from a community QA website such as Yahoo Answers. Similar to Berger-Lafferty, who pioneered this approach in IR, we use Model 1 to quantify the strength of association between query terms and terms from respective relevant documents. So we basically aim to find some, sort of synonymy. Okay, so let's look at few sample associations learned from the actual corpus of community QA corpus Yahoo Answers. So I present them in this table. In the first row, I show question terms, and the remaining rows are for answer terms with respective translation probabilities. So, and I obviously show you only the 3 terms with highest translation probabilities. So let's look at row 2. Here we can see that the word latte is strongly associated with words milk, coffee, Starbucks, and espresso. So our models, you can see that this model successfully learns various, well, so to speak, semantic relationships such as hyponymy or meronymy. To compute IBM Model 1 score, computation of IBM Model 1 score involves 2 steps. First, we need to obtain a translation probability for every pair of question and answer term. And then we need to aggregate these all pairwise translation probabilities into a single score. In fact, exact computational details are not especially relevant for this discussion, but it's important to understand that operation of just retrieving all pairwise translation scores is actually computationally expensive, and we use algorithmic tricks to make it faster. Okay, let me now talk about experiments. So I use several QA collections which contain a large number of questions. For each questions, usually for most questions, I have several passages which may provide an answer, and I call them answer-bearing passages. Okay? But I also may have passages that are not associated with any questions. I run 2 sets of experiments, exploratory ranking experiments to figure out which similarity models work well, and also actual tests where I measure efficiency, effectiveness trade-offs of the candidate generation approaches, including methods for k-NAND search. So here I present 4 collections that I used in my experiments. So 3 are community QA collections. These are Manner, Comprehensive, Stack Overflow. Manner and Comprehensive, these are both parts of the Yahoo Answers collection. Manner is a small subset of Comprehensive that is used only for re-ranking experiments. Stack Overflow is a rather well-known community QA collection related to programming questions. They often contain questions and answers, often contain overlapping code snippets. We actually exclude them to make retrieval a little bit harder. All right, and the squad is based on the Stanford Squad collection. The Stanford Squad collection consists of questions posed by crowdsourced by mTurkers to Wikipedia passages. And the set of passages used for the original Squad collection is actually quite small, and we expand this set by adding basically all the remaining Wikipedia passages, for which we actually don't have any questions and answers. So you can see that all collections except Manner are sizable. They have a large number of questions, a large number of passages, at least 10 million. Oops. Turns out that designing an effective similarity model is quite an enterprise, and I had to carry a lot of experiments to figure out which model can beat BM25 by a good margin. And unfortunately, I tried different approaches. I tried a combination of BM25 plus Model 1 for different textual representations, for representations that use only lexical features, for representations that use linguistically motivated features such as semantic row labels, dependencies. I tried question type features, and I hope that Model 1 will find associations between question types or focus words and entities extracted from passages. And basically, oh, I also tried cosine similarity between dense representations, including average word embeddings. I also actually tried doc2vec implementation of GenSim. None of that was anywhere near to BM25 plus Model 1. So I do include most results in this presentation, but I am actually going to skip them unless we want to come back. Yeah.
How stable are these experiments? That is to say, you just described running a whole lot of experiments. How confident are you that this ordering that you got is actually statistically reliable?
Very confident, because these are very that's really good point. One advantage of using community QA data, it's not so you have relevant or what you consider relevant answers, and you have really a lot of them. So basically, none of these experiments used less than 10,000 question-answer pairs. So these results, and I didn't compute statistical significance for all the results, but I'm pretty sure these results.
I'm just wondering, like, the stability of like using different random seeds and running the same training.
It's all very, very stable, because these experiments actually used really a lot of, I ran really a lot of experiments, and basically I never saw the case that it changes a lot. And I used development, I used 2 development sets, and it was all very consistent. Yeah.
Did you try any other ways of averaging the word representations? Or was it just like a uniform average?
No, it was IDF-based average.
Okay.
I also tried to several approaches. I tried off-the-shelf embeddings, several types like glove, original Word2Vec embeddings released by Google. I tried to retrofit them. This gives a little boost, but the boost is actually a very small one, maybe a couple of percent. And I also tried doc2vec, as I mentioned. Well, basically, and this is consistent with some other research, if you use just word embeddings or just doc2vec, for ad hoc retrieval, the results are pretty bad. You can combine them with, say, BM25, and you will get maybe 10% on top of BM25, which is nice, but it's not good enough to apply KNN search algorithm, because the approximation will basically destroy this, advantage over BM25. Okay, any further questions?
No, we have lots of questions. We want to let you continue because you're run out of time. Please.
Okay, I was told that was going to be like 40 minutes presentation, because we're nearly done.
Good.
Okay, so basically,
Sorry,
oh, sorry.
I'm actually dying to know. Does Elasticsearch support BM25, and are we using it instead of? Is that what we're?
It does. It does.
Is that what we're using or not?
It's one of the signals in our ranking.
But it has somewhat inferior implementation. Lucine's BM25 can be like 10% worse than good BM25. But it doesn't really matter if you rank the output of Lucene using more stronger model. It's still good enough to retrieve candidate records. Okay, so let me show you one set of results for the ranking experiments, because I think it's remarkable in the sense that I show you the difference in accuracy, the gains of accuracy they can get for parallel corporal of different sizes. And I show you here because actually most publications use 100,000 question-answer pairs to compute Model 1. I believe that leaves a lot of performance on the table. So here I have results for Yahoo Answer Comprehensive Stack Overflow, 2 subtables. The left subtable is for Yahoo Answer Comprehensive. The right subtable is for Stack Overflow. The first column in each subtable is the number of QA pairs used to train Model 1. The second column is effectiveness using the well-known expected reciprocal rank. The third column is the gain over BM25. So let's look at the first row here, and we can see that if you use dozens of thousands of QA pairs, we can get an improvement over BM25, but it's rather modest. But if we use all available data, we can get 20% for comprehensive and 30% for Stack Overflow on top of BM25. And I would say it's a strong result. And what is remarkable here, it's not, it's how far you can get. And it's definitely not in new knowledge that getting more, using more data can dramatically improve performance of your machine learning model. But I think it's remarkable how much you can get from using millions of QA pairs instead of thousands, okay? And I haven't seen this in prior publications, actually. All right, so I am going to skip a lot of slides which were, just in case, included. And I will jump, yeah. As I mentioned, our second, but don't worry, there is going to be no technical description, so we'll stay on time. So as I mentioned, we need, our second grand challenge is to implement a very efficient algorithm for KNN search. So which algorithm should I use? LSH? No, I'm using very obscure algorithms. One is called proximity SW graph, which stands for small world graph. It's a graph-based search algorithm. And another is, the second one is a pivoting algorithm called neighborhood approximation index on app. So why would I use these algorithms? And there are two simple reasons for this. First of all, this is a simple distance-based method that work for non-Euclidean, non-metric, and sometimes for non-symmetric distances. Well, coming back to your questions, how generic it can be. Well, pretty generic, more generic than some other approaches. And also, in many cases, they either SW graph or NAP, they beat state of the art even for the Euclidean distance. And that's especially true for the graph-based search algorithms. Okay, so I skip the technical details of these algorithms unless anybody wants to know them there. And I will jump right into the description of my experimental results, where I show you the efficiency effectiveness trade-offs of several candidate generation approaches, including methods for KNN search. So here, in this plot specifically, I show you the results for Yahoo Answers Comprehensive. Efficiency, unfortunately, I can't use the laser pointer. Well, efficiency is on the y-axis. It's in milliseconds per query. It's the log scale. Effectiveness is on the x-axis. It's expected reciprocal rank. And in these plots, lower and to the right is better. Okay, I use different colors to denote different similarities. Blue is for BM25. Black is for BM25 plus Model 1. I have multiple KNN search runs associated with the same method. And the reason is because I vary methods parameters to obtain different efficiency effectiveness trade-offs. So blue diamonds here, these are NAP, neighborhood approximation index, and the similarity is BM25. Black diamonds is also NAP, but the similarity is BM25 plus Model 1, which is much more expensive. So these stars here, and remember that the lower and lower to the right is better. These are runs for SW graph, and these are denoted by black stars. Approximate KNN search runs are compared against several baselines. One is just brute force exact KNN search, which is super slow. This is blue pentagon for BM25, and the black pentagon for BM25 plus Model 1. And this is just, taking dozens of seconds per single query. Another baseline is an efficiency baseline. This blue square here is C++ reimplementation of Lucin's algorithm that doesn't use compression and keeps everything in memory. But it also uses BM25. It's here, and I also have an effectiveness baseline, which is Lucene, which is used to generate 100 candidates, which are later re-ranked using similarity BM25 plus Model 1. Okay, and ideally, we want to be more efficient than this blue box and more effective than this black triangle. Okay, the first thing to note is that, as I said, brute force KNN search is horribly slow. Look at these pentagons here and here, but approximate algorithms are much faster, and the degree, and then they are actually pretty accurate. In some cases, we don't lose more than 10% in ERR. And second, I believe that this plot actually supports my conjecture that using a more complex similarity, ranking stage similarity in the retrieval algorithm can be beneficial. And you can see this from comparing blue diamond runs and black diamonds run. They're basically the same methods with the same set of parameters, except these are two identical pivoting algorithms, but they use different similarities. So this one uses much faster similarity BM25, and these runs are using much slower similarity BM25 by Model 1. But look, for example, at this black diamond run. It's about twice as efficient as all the blue diamond runs, but it's about 10% more effective. So let's now look at the results for Stack Overflow, which are in general similar. We have the same setup, the same colors, the same shapes for the search methods, but I would ask you to look at these stars here, which are runs for the method SW graph. So these runs are about like twice as efficient as the C++ implementation of Lucene, and they seem to be slightly more accurate than the than the ranking approach based on Lucene, although this difference actually is not statistically significant. So they're probably roughly as accurate. Okay, and the results for Squad, they're kind of similar, but the performance of KNN search is much less impressive here. Okay, jumping right into the conclusions. Based on these experiments, I make 3 conclusions. First, generic KNN search can be reasonably efficient and accurate in ad hoc retrieval tasks. Second, I think it supports the idea that it can be beneficial to take some ranking stage signals and incorporate them into a retrieval/candidate generation module. But there is also a negative result, which I kind of didn't discuss in details. Basically, nearly all of the results that we can find using k-nearest neighbor search, we can obtain using TF-IDF retrieval module with subsequent re-ranking. Well, I think it may be possible to do better, and I actually hope for this, but to demonstrate this requires more work on, one needs to work more on the modeling side, and this remains for future work. All right, we have come to the conclusion. Thank you very much for your attention. I welcome your further questions, but please know that the code is on GitHub. The nitty-gritty experimental details are actually in the thesis draft if anybody is curious. All right, that was it. Thank you.